it is clear that some of the layers has been shortened while some of them are elongated. So at a level between top and bottom of a beam, there will be a layer which is neither shortened or elongated. This layer is known as neutral layer or neutral surface, which has been shown over here in this figure by NN dash. Means NN is equal to NN dash, and it is to be known as neutral layer or neutral surface, as this layer is neither shortened nor elongated. This top layers are under shortening part and this bottom layers are under elongation part. So the line of intersection of the neutral layer on a cross section of a beam is known as neutral axis. So I will define once again the definition of neutral axis. The line of intersection of the neutral layer on a cross section of a beam is known as neutral axis. The layers above NN have been shortened due to the decrease in the length of the layers above NN. These layers will be subjected to the compressive stress, while the layers below NN, that is the neutral layer, have been elongated. Due to the increase in the length of the layers below the neutral layer, these layers will be subjected to the tensile stresses, as we are referring the particular figure. So here it is to be noted that the top layer has been shortened maximum, hence compressive stress will be maximum at the top layer, and if we proceed from the top to the bottom, this compression stresses will be reduced and will be zero at neutral axis. Similarly, bottommost layer has been expanded maximum, hence tensile stress will be maximum at the bottom layer. As we proceed from bottom layer to the top layer, that is specifically neutral layer NN, the increase in the layer decreases, hence amount by which layer increases or decreases in length depends upon the position of the layer with respect to the neutral layer NN. This theory of bending is called theory of simple bending. So I wish you have understood very clearly what is the theory of simple bending. So let us revise within two statements, refer this particular figure clearly. Because of the external loading, the top layers are shortened, and because of that, compressive stresses will be developed. Bottom layers are under stretching, tensile stresses will be developed at the bottom layer. At a particular layer, there is no effect of stretching or shortening is known as the neutral layer. Now, this top layer, which is maximum shortened, so maximum compressive stress will be developed at the top layer, while the bottom layer is stretching maximum, the maximum tensile stresses will be developed at the bottom layer. Now, let us go for the derivation of bending equation. Now, an equation that we have to derive, certainly sometimes it is to be called derive bending equation, or it may be says derive the equation for bending stress also. So let us refer the particular figure over here. A part of a beam that we have to discuss right now, and two cross sections AB and CD are under observation. A part of length of that beam is delta x. So figure first A shows a small length delta x of a beam subjected to a simple bending. Due to the action of bending, the part of length delta x will be deformed, which is shown in this figure number 2. This is the part of deformation. After the loading, this figure can be observed over here. Let A dash B dash and C dash D dash meet at O. Once again refer the previous figure. This A dash B dash and C dash D dash, if we are extending these lines, are meeting at point O, means from distance from point O to this neutral layer is the radius of curvature R. So R is the radius of neutral layer N dash, while theta is the angle subtended at O by A dash B dash and C dash D dash produced. If you are referring the previous figure, see clearly theta is the angle subtended between these two layers A dash B dash and C dash D dash, while R is the radius of curvature. Now first part, the strain variation along the length of the beam. Consider a layer EF at a distance y below the neutral layer and N. See, refer the particular figure. Let us consider the layer EF. This layer EF before bending at distance y from neutral layer. Similarly, this layer is E dash F dash after bending at distance y from the neutral layer. After the bending, this layer will be elongated as E dash F dash. Now, the original length of layer is delta x. Also, the length of neutral layer is delta x. That is before application of external load. Now, after bending, the length of neutral layer N dash will be remains unchanged, as the name itself neutral. Neutral means not affected by any kind of external load. So the length of the neutral layer remains same as delta x. But the length of layer under observation, that is EF, which becomes E dash F dash after the application of load, will be increased. Please precisely understood, very carefully understood with the previous figure. Now the length of neutral layer, the length of layer EF is delta x before the application of load. But after the application of load, the length of N dash is remains same as NN, but the length of EF will be increased. That length is increased because it is bottom of neutral layer. So now from this particular figure, it is clear that this N dash is equal to R into theta. Theta is the subtended angle, R is the radius of curvature. So nn dash is equal to r into theta. What is nn dash? Is nothing but our nn, and that is nothing but delta x. So finally we achieve delta x is nothing but r into theta. But what is E dash F dash? Is nothing but r plus y into theta, because y is the additional distance depth from the neutral layer. So we know that delta x is equal to r into theta, but E dash F dash is equal to r plus y into theta. Hence, the increase in the length of the layer EF is equal to E dash F dash minus EF. It is interesting point. What is our intention? Our intention is to find out what is the increase in length of the layer. If you are referring the previous figure, clearly this is the EF layer. If you are reading the first figure, this is EF layer. This is the layer E dash F dash. As we told previously, because of the loading, external loading, this is in the pure bending action, there will be a certain increase in the length of the layer of E dash F dash. What is that? It is nothing but E dash F dash minus EF is nothing but our increase in the length of the layer. Now, we know the value of EF, because the length of EF as well as length of NN as well as length of N dash N dash is remaining same as of delta X, and that we found out as R into theta. Yes, over here. So E dash F dash minus EF is equal to, we know the E dash F dash is equal to, that we found out here, r plus y into theta minus this EF is nothing but r into theta. So if we are do the simple calculation, we got the increase in the length of the layer EF is y into theta. This is nothing but increase in the length of the layer. So what is strain? So strain in the layer EF is nothing but change in length by original length. Strain is defined as change in length divided by original length. Now here change in length is nothing but increase in the length of the layer EF divided by original length. So what is the increase in length? That we found out as y into theta. What is original length? It is nothing but r into theta. That is nothing but neutral layer length, that is delta x. So we got strain in the layer is y divided by r. What is y? Y is the distance of a layer from neutral axis or neutral layer, while r is the radius of curvature. So I will repeat once again the statement that y is the distance of a layer from neutral layer. If you are referring the previous figure, clearly see the figure. Y is the distance of a particular layer from the neutral layer, while r is the radius of curvature. So we achieve an equation strain in the layer EF is y by r, as r is constant. Hence the strain in a layer is directly proportional to its distance from the neutral axis. Very much important observation that we found out over here right now, that the strain in a layer is proportional to its distance from the neutral axis. Neutral axis y is high, strain in the layer is high. Y is less, strain is less. So the above equation shows that variation of strain is linear variation of strain is linear. That is a most important observation that has been found from this equation. Now next, part B, that is the stress variation. Let F is the stress in a layer EF. See the previous figure. We found out the strain in a layer. Now let F is the stress in a layer EF. E is the modulus of elasticity of the material that has been used in a beam, and we assume homogeneous material. So modulus of elasticity of a material is constant as per the assumption number 2. Hence, what is the definition of E? Modulus of elasticity E is defined as the ratio of stress versus strain. That is stress in the layer EF divided by strain in the layer EF. So, if you are putting the value, E is equal to F divided by Y by R, that has already been established equations previously. So, if you simplify this, then F is equal to E into Y by R. So, we got an equation, F by Y is equal to E over R. F by Y is equal to E over R. In other words, F is equal to E by R into Y. Very much important equations, and please see these observations very clearly, that in this equation E is constant in a beam, R is also constant, means F is directly proportional to the Y. What is Y? Y is the distance from neutral layer or neutral axis. As Y increases, stress is also going to increase. If Y going to reduced, my value of F goes reduced. So, we achieve one single equation right now, F by Y